9-3, arcs and central angles. Here we go. Ready? All right. So, central angles. Yeah.
I was just wondering, is it like, would it ever be a possibility to like combine all the quizzes into a test so we have more time to like work on?
That sounds like an excuse terrible.
I'm sorry,
Absolutely not.
Yeah.
It gives us more time with the material.
Yes, but then I have to memorize a lot of material all at once.
The problem is,
Like I understand we're like pressed for time. I just feel like
well, I think now if we finish the material today and you don't have the quiz until Wednesday, that gives you all of today. Tomorrow's my late day, so you could stay after. I think that'll be fine.
Yeah, the way it's being
And you guys got 65 bonus points, so I don't really feel all that bad. Okay, let's go. Central angle. An angle whose vertex is at the center of the circle. You're going to love central angles because they're so easy. So a central angle, literally, right? I have my center point, so let's call it A, for example. And then if I just make two radii, so we'll call that AB, and then another radius wherever you like, it doesn't really matter. You have just formed a central angle. Okay? It's an angle whose vertex is on the center of the circle. Okay? So that thing right there is called a central angle. Now, we know that we measure angles in degrees, right? Of course, because we've been doing that quite a bit. How many degrees are there in a full circle? 360. So, I can talk about this angle being in degrees like I always have, but then I can also talk about this arc. So, what is an arc? An arc is just a piece of the edge of a circle. Okay? So, this arc right here, I would just name it BC, almost like I'm naming a segment, but it's not a segment because I'm not going straight from B to C. I'm going along the curve. So that would be referred to as arc BC or arc CB, it doesn't matter, because it's the same thing, just that piece of the circle, okay? And I can talk about the arc being measured in degrees too. The nice thing about it is it's exactly the same as whatever the central angle is. So if I measured this and found out that it was 70 degrees, then arc BC would have a measure of 70 degrees. So central angles, and this is referred to as its intercepted arc. So the arc that's formed when I draw that angle is its intercepted arc. They are the same. Okay, so now let's go over these things. Central angle, yep, we already talked about that. Arc, part of a circle formed by the intersection of a circle and a central angle. So, that's what we were just talking about. If I draw my radii, I've now sectioned off a piece of the circle in between those two endpoints, referred to as an arc. Okay, there are different types of arcs. There's a minor arc, a major arc. Well, let's before I keep going, what do you think the difference is between a minor arc and a major arc?
major arcs are more
Is
proportionally
it the big
Like
size
acute
of
and
the rest?
obtuse except minor and major.
Kind of, yeah. So a minor arc would be less than half the circle. So its measure would have to be less than, what would the measure of half a circle be? 180. So it would have to have a measure of less than 180 degrees. Whereas a major arc would be, yep.
Wait a second. So when you say arc BC, how do you know you're not referring to like B all the way around?
Great question. It all comes down to the naming. Does everybody get her point? She's like, if you say arc BC, how do you know it's just this and not this? So, when you name an arc, if it's a minor arc, you just use the two letters. Just whatever the two endpoints are. So if you ever see an arc that's named with just two letters, you know it's a minor arc. So you know you're taking your shortest route, well, along the edge of the circle between those two. Okay? Now if I wanted to talk about this big old arc out here, that would certainly be a major arc because it's more than half my circle. In order to name a major arc, you have to use 3 letters. So where does the third letter come from? Well, you'd have to have some other point along the way. So let's say that's point E. So you would just name it BEC or CEB. Okay? So it's still the same 2 endpoints, and then it's any other letter that you pass along the way. So if you had another point here that was F, you could say CFB or BFC. Doesn't matter. You need your 2 endpoints and then someone that's passed along your route. Okay? So let's get all this down. So a minor arc. I don't really have enough room here. I'm going to put it down here because I have nothing else that I need to write there. So minor arc measures less than 180 degrees, and you name them with 2 letters. Named with 2 letters. Well, let's say the 2 endpoints. And here's something else that's super important, so watch this. So if I wanted to write arc BC, you can either write the word arc BC or you do this. You put a little arc like that. That is different than this, right? That would refer to segment BC, and that's not what you're talking about. So if you're naming an arc, you got to put an arc over your letters. Like I said before, it could be CB. It doesn't. Your order doesn't matter. So that's your minor arc. Then we have the major arc, whose measure is greater than 180. And they are going to be named with 3 points. And you have to have the outer 2 are the endpoints. So, for example, arc BEC. You guys see this okay? All right, so there's major arc, minor arc. What happens if you have an arc that's exactly 180? Well, that's true. We call it a semicircle. Why not a hemicircle? I don't know, because you have hemisphere, right? And it's not semisphere, it's a hemisphere.
Hemi is like for 3-dimensional, while semi is for 2-dimensional.
Maybe. Yeah, I don't know. So, semicircle.
Glass, which is 2D, not really, is semi-transparent. Nothing is.
So, semicircle measures exactly 180. How do you suppose we name those? Do you think you use 2 letters or 3 letters? You still need 3, and this is why, because what if, so if I had A, right, if I had a diameter here, if I wanted to be this side and not this side, so you still use 3 just to designate which side you're going on, okay? So we're still going to name it with 3 letters. Why am I messing up my M's today? I don't know. Named with 3 letters. Yep. Yep. So this would be semicircle ACB, for example. And then adjacent just means the same that it's always meant, right? Remember when we had 2 angles that were adjacent to each other? They're just like next door neighbors. They don't overlap each other. They just had like the side down the middle that they shared. So it's very similar with arcs. They're just arcs that they share one endpoint with each other and they don't overlap. So arc AC and CB would be adjacent arcs. You follow me? Let me zoom in a bit.
What kind of adjacent adjacent angles, because if we start from the center point.
Your central angles would be adjacent, absolutely. So let me throw in an extra point on here. Let's say I had point E. So there's A. Is arc AE adjacent to arc CB? No.
Vertical arcs?
Nope, so just the arc. So this arc AE and arc CB, they are not adjacent to each other. They have to share a common endpoint, and they don't. Okay, how about this? Arc CB, is it adjacent to arc BEA? Yes, they would be. They share B. What do you suppose is true about arc CB plus arc BEA? It would be equal to the measure of arc CBA. Doesn't that make sense? If I took this one and I added this one to it, wouldn't I get the whole thing from here to here? Yeah, that's basically all the arc addition postulate says. So if we look back up in our notes here, arc addition postulate, if two arcs are adjacent, their sum is equal to the arc formed by the two adjacent arcs. Yep,
I have a kind of random question.
it's okay.
So, I know someone was going to talk about ovals, but I just have a question. So,
That's
like,
okay.
It's so like it adds up to 360 all the measures within an angle. Is it like do all the measures of an oval also add up to 360? Just because like it goes all the way around, but then like it's not like a circle.
No, because I don't think you can measure an oval in degrees that same way. Yeah, I don't think so. You can measure its length. So the length of a circle, like if you actually walked in a circle, you would never talk about that in degrees. Like imagine our track was a circle, right? If you went out and walked a lap, you wouldn't say, wow, I walked 360 degrees. I feel so good, right? You would never say that. You would say, oh, I just walked a mile around the track, right? So there's something called arc length, which is the actual distance if you actually went around that. So you would have I don't know if you even call it arc length, honestly, but you could find the length of an oval, but it wouldn't be measured in degrees. Yeah. So fast. Okay, so back to my adjacent arcs business. So let's just throw some numbers on here so we know what we're talking about. C, D. Okay, so you see my picture here? Let's say that arc CD was, oh, I don't know. Let's say it was 100 degrees. And let's say that arc DE was 30 degrees. What's the measure of arc CE?
130 degrees.
130. That's all this addition postulate is saying. If they're adjacent arcs, I can just add them together. Okay. What is the measure of major arc CEB?
310 degrees.
Ooh! Where did he get 310 from?
Wait, can we assume
I added
that
130
B-
degrees to 180 degrees because from B to E, since it's a diameter, would have to be a 180 degree arc.
Exactly.
Can we assume that we like? I'm just
Can you
wondering,
repeat
like,
that?
just in general, can we always like?
Yes, if a line, a chord, goes through the center, it has to be a diameter. So that means that this arc right here, BFE, is actually a semicircle 180 degrees. So you could either go 100 plus 30 plus 180, or if the only thing that's not included is BC, right, I could just do 360 minus whatever that's got to be. And how do I know what that is? Well, if this is 180, isn't this also 180? So that's got to be 50, right? So I could just do 360 minus 50 if that's fast or whatever. Float your boat. Okay, so that's that. We already mentioned the measure of an arc is equal to its central angle. So equal to, let's cross out to the, it should just be its central angle. Two arcs are congruent if they have the same measure on the same circle or congruent circles. Okay. So that's pretty straightforward. So if I had something like this. If I had this diagram back and I knew that BC was 40 degrees and DE was 40 degrees, that means that these arcs are congruent because they have the same measure. Easy enough? Okay. All right. So, oh my God! How am I going to get through 9-4? Crap! Jeez.
Time for nitros.
Jeez, the squeeze. Okay. No, we don't have time. We can't stray. Okay. So, I'm going to get as far as I can. It is what it is. I got 6 minutes. I can do a lot in 6 minutes. Ready? Okay. All right. So I'm going to start off with a circle. Okay? If I have in a circle or in two congruent circles, so it doesn't really, I mean, I guess we could draw two of them. All right, fine. What the hey? So if I have two circles and I know they're congruent to each other, right? If I have, let's draw the centers in each one. If I have a central angle here, and it's congruent to a central angle over here. So I'm actually going to draw it a little bit differently so they don't just automatically look the same. If that's true, well, then doesn't that mean that arc AB and arc CD have to be the same? It has to be. If they are congruent circles, first of all, doesn't that mean that their radius is the same? Their radii, so all their radii would be the same. So this would be the same as this, would be the same as this, would be the same as this. Okay? So if their central angles are the same, this is basically the same circle, right? So this, if that's 80 degrees, that would be 80. So if that's 80, that's 80. So arc AB would have to be equal to arc CD. Now, you ready for this next part? If I drew in the chord that connected those 2 points, so AB, so if I drew in a straight line from A to B, that's chord AB, and I drew in chord CD the same way, what do you know about those two chords? They have to be the same. And basically, it's all interchangeable. So, if I started off a little bit differently. Let's say I know I have two congruent circles, and then I knew something like A, B, C, D. Let's say that I knew that this chord and this chord were the same. And that's all I know so far. I have congruent circles that have congruent chords in them. Well, guess what? If I just go ahead and draw in the central angle that creates that chord, same thing on both. What do I know about those central angles? They have to be the same. If I know any one of the three pieces, if I know that the chords are the same, the central angles have to be the same. If the central angles are the same, then the arcs are the same. So now I also know arc AB has to be the same as arc CD. So they're all interchangeable. If I have any one of those three pieces, I know them all. And it works if I'm just looking at one circle. So check this out. So real quick, if I knew in just this circle that, let's see, what should we do this time? Let's say I knew that the arcs were congruent to start off with. Yeah, sure.
I can watch the video.
Okay. So, first of all, I always know that all the radii are the same. That's always true. If the arcs are the same, don't the central angles have to be the same? Yes. And then if I were to draw in the chords, they would also have to be the same. So I get all of these pieces kind of for free. Does that kind of make sense? Okay. Oh, this is so cool. The next thing says, if you have a diameter or a radius, it doesn't have to be a diameter. If it's perpendicular to a chord. So if I draw in any old chord, and this is perpendicular, guess what the diameter just did to that chord, chord AB? Yes, it bisects it. Wow. Okay, so let's put that on our sheet here. Where's our sheet? Here it is, here it is, here it is. If a diameter is perpendicular to a chord, then the diameter bisects the chord.
What did that picture look like?
And then the very last thing says, in a circle or congruent circles, if two chords are equidistant from the center. So imagine this. I have a circle. Can I go away from this now? I have a circle. I have two chords that are both equidistant from the center. So I have that thing and I have this thing. If I find their distance to the center, that distance and that distance, remember you always measure distance as perpendiculars, if those are equal to each other, what do you think has to be true about my chords? Yes, AB, chord AB and chord CD must be congruent. So when you're filling the blank, you just put a congruent symbol there. Oh wait, no, I'm sorry, we're up here. If two chords are equidistant from the center, then they are congruent. Excuse me. And then the last thing, if two chords are congruent, guess what? They must be equidistant from the center. They are equidistant from the center.
Can you go back to the picture, please?
To what?
The previous picture for the previous. Thank you.
So, real quick, that one is showing you if I know that my chords are the same. Right? So if I know that, that's saying, okay, well now they must be equidistant from the center. So if I drew in those perpendiculars, they'd have to be equal to each other. Oh dear. All right. Yes, my gosh.